Alright, so this video is about inscribed angles. You remember from the last video, this is what an inscribed angle is. By definition, an inscribed angle is an angle whose vertex is on the circle. You may also remember that what we said was whatever this angle is equal to half of its arc. Alright, so just keep that in mind. Let's talk about this. This angle is half the measure of its arc. Right now, take out a sheet of paper or whatever and just draw a circle. Just some circle. Pause the video. On that circle, draw a line that intersects the circle twice. So these are the directions. On your circle you just drew, draw a line to intersect the circle twice. So you can figure out how to draw a line that intersects the circle only twice. You probably do something like this. The line hits it here, hits it twice. The name for a line that intersects the circle twice is a secant line. Alright, so it's a line that touches the circle twice. Pause the video again, and this time draw a different line. This line is only going to intersect your circle once. So see if we can figure out how to draw a line that only touches your circle in one place. Do that now. A little bit hard to figure out, right? You may eventually drew something like this, though. Some line that didn't actually go through the circle, just barely skimmed the circle. Like it's barely tapped it. There's a name for that. That line is called a tangent line. Kind of like the words you learned when you took geometry, the trig section, learned about secants and tangents and cosines and sines. Whenever that word comes back, it's called a tangent line. And a tangent line touches the circle in only one place. What's neat about a tangent line is, if you have a radius of a circle, and that radius touches the tangent line, they meet at a right angle. So if you've got a radius of a circle, and it touches the line that's tangent to the circle at the same point, we have a theorem that says they meet at a right angle. Nice thing to know, I'll write that down someplace, that the radius and the tangent meet at a right angle. Alright, I'm about to erase all this stuff, so if there's anything you didn't already know, I'll write it down. Alright, new theorem. This theorem deals with, this is a chord of a circle, and this is a tangent to the circle. The theorem says that if a chord and a tangent intersect at the same point on the circle, then the angles are equal to half the arcs that are formed. So angle 1 is equal to half of this arc. Angle 2 is equal to half of this arc. Alright, so that's the theorem. So the theorem says if a chord and a tangent line intersect on the circle, or again, if a chord and a tangent line intersect on the circle, then the angles formed are equal to half the intercepted arc. So that's the word I didn't mention so far, intercepted arc. What I mean by intercepted arc is that this is one side to the angle, this is the other side to the angle. Arc intercepted would be from here to that point of tangency. So that's its intercepted arc. Arc goes along with 2, we'll start from here, come down to this point of tangency. Alright, so those are the intercepted arcs. These are arcs formed by those angles. So that's a theorem. I'll get that down. Got a new one. Let's say we got this circle here, and his name is T. This is circle T. I suppose we got 2 chords. This is one of the chords. Here's the second chord. Notice they don't really meet at any point special. They don't meet at the center. There's no name for that point. Meet. There's no special place for it. All I know is we got 2 chords. Let's name it chord W, L, Y, Z. Alright, so those 2 chords, W, L, and Y, Z. What I know is I got angles here, 1, 2, I call those angles 3 and 4 if I want. And I know these 2 are vertical angles. Alright, so we got a theorem that says this. If we have 2 chords that intersect on the inside of a circle, then the sum of their arcs divided by 2 equals to one of those angles. So the verticals, both angles are congruent anyway. So the theorem says this. Alright, so what I have is this. If 2 chords intersect in the interior, or the problem is exterior. So it's the interior of the circle. Well, it could be 2 chords anyway, meeting outside the circle. If 2 chords intersect in the interior of a circle, then the measure of each angle is half the sum of the opposite arcs. So what I mean is this. Let's say this angle was 100 degrees. This arc was 100 degrees. Let's say this arc is 40 degrees. All right. So one is smaller than the other. And what I know is measure of arc WY plus the measure of arc ZL divided by 2 equals the measure of angle 1. So I know that 100 plus 40 divided by 2 equals the measure of angle 1. So it's 140 divided by 2. That's 70. I'll put it someplace else. 70 equals the measure of angle 1. 70 degrees. So if angle 1 is 70 degrees, for the vertical angles, angle 2 also has to be 70 degrees. That's how vertical angles work. So now, that's a degree sum, that's 1. So anyway, that's what that theorem says. That if I want to find either of these angles inside that triangle, I can simply figure out what the arcs are, the opposite arcs there. And if I know those two, I can figure out other arcs. Like if I knew this was 70, I know this has to be 110, and that's 110. And, I can figure out these arcs and everything else around if I wanted to. All right, so anyway, that's it. New theorem. All right, suppose I had an angle formed by a tangent line. All right, so it's a tangent and a secant. Or if I had a line, two tangents formed. Angle formed by two tangents. Let's call this angle 1. Call this angle 2. Or if I had an angle formed by two secants. They all got something in common. Call this angle 3. All right, so if I have an angle formed by a tangent and a secant, two tangents, two secants. All of the angles are equal to is not the sum of those arcs, but the difference of those two arcs. So let's give these arcs names. Let's say this is M, N, O, P. All right, so if that's a tangent, it only meets at 1 point, so we don't need the P. And let's get this arc again. Let's say this is M. No, P use M twice, so we just got it. Let's say this is T, W, X, and let's say this is A, B, C, D. All right, so what I know for certain is the measure is equal to the measure of arc, NO, all right, so NO, subtract MO divided by 2. All right, so if I subtract the larger one and the smaller one and take it in half, I know it's going to equal the measure of angle 1. For that matter, if I was looking over here, looking at this one, I know the measure of angle 2 has equal to this major arc here, measure of arc T, W, X, subtract, let that look better, measure of arc T, W, X, subtract, so it's a bigger one, subtract the smaller one, TX, the measure of arc TX, divided by 2. And same case to this last one, I know the measure of angle 3 has equal to arc BC, subtract arc AD, divided by 2. I take it I should have a little M for measure in front. So measure those arcs divided by 2. So if I knew those parts was, I could simply find them by taking the bigger arc, subtract the smaller arc, divided by 2. And that gives me the angle, an exterior of the circle. All right, so there's a theorem for all of that that explains all those. I will get all those little formulas down as notes because it may be useful later. The theorem's in words, this is in symbols. One of them may be more useful to you than others. So before I erase a lot of this, I'll copy down everything you didn't already know as a note. If a tangent and a secant, or two tangents, or two secants intersect outside of the circle, measured in the exterior of the circle, then the measure of the angle is equal to half the difference of the intercepted arcs. So take half the distance. Don't add them. The difference of that and divide by 2. All right. New example. All right, up until then, we're talking about angles. Let's talk about segment lengths. All right, let's say we got 2 chords. This is a chord, call it E, T. This is another chord, we'll call it L, O. Let's put a point in the middle where they intersect. Let's call that point J. All right, basically what we know is if those 2 chords intersect inside of a circle, then the parts there have equal products. So segment EJ times JT is equal to segment LJ times JO. It's pretty neat because if I had some circle and 2 chords intersected there, let's say this piece was X, this piece was 2, this piece was 3, this piece was 5. That's an X, not a 4. Well, I know that 3 times 5 has equal to X times 2. So 15 has the equal to 2X, and 7.5 has equal to X. So I can figure out what X is because I know those products have equal to each other. All right, nice little theorem to know. Another theorem is this one. Basically, this theorem says that we have 2 secants. Right, this is one secant. This is another secant. Let's give it a name. Let's call it N, K, J. Let's say this is W, and B. All right, so those are letters for it. So basically, the theorem says that if I got 2 secants that intersect outside the circle, then segment NK times the entire segment, NK times NJ, is equal to NW, it's small piece, times the entire piece, times NB. Equally nicely though, for the same reason as the last one. All right, so this is always true whenever you have 2 secants that meet outside the circle. All right, so for example, we had this circle going on, I had these 2 segments happening. Let's say this segment was X, let's say this segment was 5, this segment was 7, and this segment was 30. Well, I know that X times X plus 5 is equal to 7 times 37, right? Because 7 plus 30 is 37. So it's a quadratic equation. This is X squared plus 5X equals to whatever 7 times 37 is. I guess it's 258. My math is right. No, 259. So 259. So I'll subtract 259, use quadratic formula, be done with it. I already know what X is. I can solve it using that fact. So it's a really nice theorem to have. Last theorem is this one. All right, so this theorem, suppose we had a tangent segment. So it only touches it once. And we have a secant segment. Let's say this is T, O, Q, J. All right, what's cool about this theorem is this segment outside, TO squared is equal to the product of TQ times TJ. I just thought it was pretty awesome. This piece squared is equal to this section times the whole length. That's what it's going to be equal to. All right, really nice little thing to know. All right, for the sake of time, I'll let you write down what those theorems actually say in tomorrow's lesson or whatever. But that's it. That's all I have for now. Good luck.